Hello students, in last video I explained how the light emitted from the two light sources, coherent sources, meet and produce bands of brightness and darkness on the screen, and the two coherent sources, as I explained, can be obtained from the single source of light, which is a monochromatic source of light. And now we are in position to find the condition under which we will obtain a bright point on the screen or a dark point on the screen, for which let us assume two sources, two coherent sources of light as. So let's assume there are two sources, coherent sources of light, that is kind of this S1. I take S1 as this is, let us say, S1, one source of light. This is S2, another source of light. When the waves from these two sources of light meet on the screen, they produce either this kind of pink or this darkness, this pink or this darkness, these bands, and these are called interference pattern. Now we have to find what is the condition of getting this brightness and this darkness. In under what condition we will find this brightness or darkness of light on the screen. For that, let us assume one wave starts from here like this, and another wave starts from here, and both these waves will meet anywhere on the screen. I assume that this wave is denoted by, let us say, y1, and this wave is denoted by y2, and when these two waves will meet on the screen, they will produce a net result of these two, let us say, that is y, and this y can be determined by a simple calculations. Let us assume y1 is represented by its amplitude a1 and sine of phi, let's say sine of omega, its frequency omega, and d. We know that a wave displacement can be represented by this equation, and let this y1 is represented by this and y2 is represented by its amplitude a2 sine of omega t plus some phase difference phi. So according to the interference theory, this pattern is produced only if when this phase difference should not be there, that means it should be 0, or when this phi is constant. So we assume that phi is constant here, and on the screen we will get some pattern when these two waves will superimpose. So using superposition principle, we can write y is equal to y1 plus y2. On substituting the values from here, we get a1 sine omega t plus a2 sine omega t plus phi. So we get these two equations from here. Now we can solve it by using trigonometric relation here for sine a plus b. So we can write here a1 sine omega t plus a2 sine omega t cos of phi plus a2 cos omega t sine of phi. So I have just expanded that simple relation, and from here mathematics we will use that sine omega t we have here, sine omega t, cos omega t we have here, but this sine omega t is also present here. So let me take this sine omega t common, so I can write sine omega t common, Inside I left with a1 here plus a2 from here, cos of phi which is left here, plus then we have cos omega t, a2 cos of omega t and sine of phi. So now we have omega t term and phi term. Let us substitute this phi term as new parameter in terms of new parameters, that is, let me write it as sine omega t, and I will put this as a cos of new parameter phi plus cos omega t into a2 sine phi. I will put equal to a sine of theta. Sorry, here I have to replace. Here I won't put phi again, I will put theta here. So here in this equation a is not known, I have to find. Theta is also unknown, I have to find the values. But using this expression I can write a cos sine omega t, a cos phi. A is common, let me take a common. Then I left with only sine omega t cos theta plus cos omega t sine theta, which can be written in terms of sine omega t plus theta. So it means I can write a sine omega t plus theta. So this is the resultant of superposition of two waves omega t plus phi. This is superposition. When these two waves superimpose on the screen, we will get a net superposition result here, and it will depend upon this a amplitude and in this theta not phi, as a is unknown, theta is unknown. So in terms of a and theta we will find these two. That means to find whether it is maximum or brightness or darkness, I should know what is a and b. So in this equation, let me mark it as equation 1. I have to find what is a and what is theta. Now from this substitution I know that a of sine theta I have substituted is equal to a2 sine of phi, and I have substituted a cos of theta is equal to a1 plus a2 cos of phi. So here let me have this is first and this is second. Let me just divide it, or on division of these two we get a sine of theta over a cos of theta, that gives me tangent of theta is equal to, on dividing, a2 sine of phi divided by a1 plus a2 cos of phi. So it gives me theta is equal to tangent inverse of a2 sine of phi divided by a1 a2 cos of phi. So we know now what is this theta in terms of initial values, that is a1 a2 and phi. Similarly we can find what is the value of this capital A amplitude. For that what we do is we square and add these 1 and 2. So on squaring and adding we get a square sine square theta plus I add this term, that is a square cos square theta is equal to, now right hand side first term I will square it, that is a2 sine square phi plus, now I will square this term, that is a and b, two terms, square of it, that means a square plus second square of second term b square, that is a2 square cos square phi plus twice a1 a2 cos of phi, and it gives me, left hand side will give me only a square, because sine square theta plus cos square theta will be 1, equal to, from here this sine square phi and this cos square phi, when we take a2 square common, then it will give me 1. So I will get here a1 square plus a2 square plus 2a1 a2 cos of phi. So this is how we can find the value of a also. But we know that the intensity of light at a point is given by square of amplitude. Therefore, because we know this point, therefore you can write that this expression is telling us that the total intensity on the screen, which we are concerned with here, whether it is this reddish point or this blackish point, that will depend, intensity will depend upon the intensity of first, because it is also a1 square, so that means intensity due to first source plus intensity due to second source plus twice I1 square root, then I2 square root here, then cos of phi. Because here also this amplitude, it is not square, therefore we'll take it as square root. So it gives me, this gives me that total intensity will be equal to I1 plus I2 plus twice I1 I2 square root into cos of phi. So from this expression it is quite clear that intensity on the screen will depend upon cosine of phi. Now the maximum value of cosine of phi is +1 and minimum value of cosine phi is -1. It means when when cos is phi, cos phi is 1, when cos of phi is equal to 1, we will get a maximum intensity here. That means I will be maximum, and when cos phi is equal to -1, then intensity will be minimum. Intensity will be minimum. And you know that cos phi will be 1 when it will happen only when phi will be equal to 0 or 2 pi or and so on to n pi, because it should be even multiple of pi. So twice n here is integer 0, 1, 2, 3, and in this condition phi should be equal to either pi, because cos 180 degree will be -1, or it should be 3 pi, that means odd multiple of pi, which means we can write 2n plus 1, that is odd number, multiply by pi. So these are the conditions for phase. If either phase should be 0, when phase is 0, then you will get maxima, which means in this case you have seen that if these two waves have same phase or no phase difference, then we will get maxima here. And if phase difference is opposite, that is it is pi or 3 pi, then we will get minimum intensity, that means we will get darkness there. Okay, so this condition we can very easily find. Now we know that the path difference is corresponding to phase difference. A relation is given by that if path difference is let us say lambda, if path difference is lambda is path difference, then phase difference is 2 pi. For example, in this wave, if you see that a wave we can draw like this, then from here to here we have full wavelength, but the phase difference from this point to this point we have 2 pi phase difference. So the relation between phase difference and path difference can be obtained from here, that path difference is simply lambda over 2 pi times phase difference. So for maxima, from this relation and by using these two relations, we can say for maxima for bright fringe, for brightness or bright point, point is fringe, you can say for bright fringe, path difference will be equal to lambda over 2 pi, and let us put the condition of phase difference of maxima, that is 2n pi, 2n pi, and from here 2 will cancel, pi will cancel, and you will left with n lambda. So for bright fringe, path difference is equal to n lambda. That is the condition. And similarly, you can find what is the condition for minima for, you can say, dark fringe. For dark fringe, path difference can be written as lambda, path difference is lambda over 2 pi multiplied by 2n plus 1. We'll putting the value of phase difference here, which is 2n plus 1 pi. So it shows that pi will cancel now. We will get path difference condition for dark fringe. We will get 2n plus 1, that is odd number, lambda by 2. That means if path difference is odd number of half wavelengths, then the point on the screen here you will get this kind of darkness, otherwise it will be a brightness. So these are the conditions under which we can find bright point and dark point on the screen. One condition is this, other condition is this. This is for the brightness, this is for the darkness. So rest of the part of interference I am going to discuss in next video. Thank you for watching.